And Hanna, you can begin as soon as you're ready.
Okay, so thank you very much. I'm very happy to present this work in such a great company of a paper presented by Brett and by Thomas. This particular work is joined with Jigao He and Jason Lee, and it is motivated by the observation that a lot of the new generation blockchains are using Byzantine fault tolerance consensus mechanism. So this is the type of a consensus mechanism that Brett referred to as a classical consensus mechanism, for example, in delegated proof of stake systems. And the Byzantine fault tolerant consensus mechanisms, they rely or they refer back to a very classic problem of Byzantine generals problem that goes back to the late 70s and the 80s. And in fact, we have well-functioning distributed databases that are using the Byzantine fault tolerant solutions and consensus mechanisms, and very successfully since they were developed in the 80s. Now we see a resurgence of interest in Byzantine fault tolerant protocols because of the increased interest in blockchains and the use in the new generations of blockchains of these BFT mechanisms. Now, there is a difference, a very meaningful difference between blockchains and traditional distributed databases, and this particular difference is of special interest for economists. So, in traditional classical distributed databases, the applications were set up within one company. So we could have nodes that are failing or nodes that are hacked, and those are the Byzantine faulty nodes. But otherwise, we would assume that the nodes are following the prescribed protocol with which they were programmed. And this is what we call honest nodes. And Brett in his talk referred a lot to honest nodes and honest participants of the system. So this is kind of an adversarial environment in itself, because we need to worry about those hackers and failing nodes. But moving from traditional databases to blockchains changes the nature of this adversarial environment, because we no longer can assume that the nodes that are non-Byzantine are just honest, because now we have validators validators in these distributed databases that are their own independent entities, and they are profit optimizing or payoff maximizing at their individual levels. They may rationally decide whether they want to follow the protocol or not, depending on the expected payoffs from following the protocol or not, and diverting from the protocol. So now we no longer have the environment with honest nodes versus failing and hacked nodes. Now we have those self-interested rational nodes that need to decide whether they follow the protocol or not in equilibrium. And on top of that, we still have the failing nodes and possibly hack nodes, the Byzantine nodes. So what we are doing in this paper, we are taking an economics lens to this shift of this adversarial environment, and we are asking what is the effect, or how this shift is going to affect the stability and performance of the system in equilibrium. So the classic fault tolerant protocols make several assumptions, and the most important ones here are that first, Byzantine faulty nodes can behave arbitrarily. We don't really know what they are going to do. They definitely do not need to follow the protocol, but we don't know in which way they are going to divert from the protocol. For non-Byzantine nodes, however, it is assumed that they will be honest in the sense of following the prescribed protocol. Most importantly, Byzantine fault tolerant protocols are devised for peer-to-peer networks where none of the nodes is more important than others. This is why we have no trusted third party, no node that holds authoritative version of the ledger of the database. Everybody is equally important. And that means that each node needs to decide whether to update its own local version of the ledger based on the local information that they are receiving from other nodes. And no entity in the system has a global view on all the information that is being sent in the system. Okay? So we recognize that in blockchain environments, the non-Byzantine nodes are not just honestly following the protocol, but they are rational payoff maximizing entities. And moreover, they are ambiguity averse about Byzantine strategies because Byzantine nodes can behave in arbitrary matters. So they can take any strategies, any probability. So we go with ambiguity aversion. Okay. So in our analysis, we are using a simple game, a simple framework that we call a consensus game. And this game is a game between a continuum of mass n of computer nodes, and it follows in a couple of stages. So first, a nature randomly selects one node as a leader, and all other nodes at this time are called backups. Then the leader decides for each backup whether to send a message, right? And the message in the context of blockchain may be a new batch of transactions that will need to be added to the local versions of the blockchain for each node. So leader decides whether to send a message to each one of them, and then each backup who received a message from the leader decides for each other node whether to forward the message. And this we call peer communication stage. For backups who have not received a message from the leader, they cannot forward the message that they didn't receive, so they can really not do anything. They have no decision to make. After the communication stage, each node needs to decide whether commit the message based on its local information, based on the number of messages that then confirmations and forwarded messages that they got. And committing on the message is equivalent to updating its own local version of the ledger with this new information. And in our picture here in the illustration, all of the nodes are committing to the message, and therefore we are reaching consensus. That means that everybody updated their ledger exactly the same way, and now we can say that they all have a copy of the same ledger. But note that this is actually a non-trivial thing. When we keep talking in the context of blockchains that there is the blockchain, there is no the blockchain. There's just many, many copies of the blockchain, and they are not being just copied from a single source. Instead, the local copies need to be constantly updated with little incremental pieces of information in a way that nodes know that everybody else has also updated it the same way. Okay? So this particular setup is a backbone of all Byzantine fault tolerant mechanisms and protocols. And yes, we can add all sorts of blows and whistles, but this would be the core that we will be using. Of course, since we are talking about Byzantine fault tolerant mechanism, we need to account for the fact that there will be Byzantine nodes who may be taking arbitrary actions and not following the protocol, or not even profit optimizing, payoff optimizing within the system. So we assume that there is, out of our measure n of all the nodes, there is a measure f of Byzantine nodes who may behave in arbitrary way. The challenge in Byzantine fault tolerant systems in Byzantine faulty systems is that we don't know which of the nodes are Byzantine. If we knew, we would just exclude them and then would proceed with all nodes that are non-Byzantine. Now, as for the remaining n-f non-Byzantine nodes, the classical Byzantine fault tolerant protocols, they assume that those nodes will just honestly follow the protocol. Instead, we say that they are rational and they are maximizing their payoff. Therefore, we need to specify what are the possible payoffs for different decisions that the nodes are making. So for each node, after the communication stage, each node is making a decision whether to commit message or not to their local ledger. And if a node commits the message and the consensus is achieved, then the node receives a reward R in that situation. However, if the node commits the message and the consensus is not achieved, that now this local ledger of this node is different than the local ledgers of other nodes, and or at least of some other nodes, and therefore the node receives a penalty C for having lack of diverging ledgers. And what do we mean by when I say that consensus that we reach consensus or that consensus succeeds? This is when almost all the rational nodes commit to a message. So if all rational nodes update their ledgers in the same way, this is when we say that we have consensus. So you can see that we have here a dynamic game with imperfect information that is in its nature a coordination game, because every rational node wants to commit if other rational nodes commit as well, and they don't want to commit if other rational nodes are not committing, with features of sheepdog, because the communication stage is not directly entering the payoffs. The payoffs are depending directly only on the commit decision. Okay. So in this context, we are going to apply perfect Bayesian equilibrium with multipliers over Byzantine strategies because of the ambiguity aversion. Okay. So our contribution here is to interpret blockchain Byzantine fault tolerant protocols within economic frameworks so that we can derive further insights and implications for system stability and system design. And the first thing that we do is we characterize all symmetric equilibria in our simple game. So we start by setting up a candidate symmetric equilibria, and then we derive conditions under which those equilibria exist. So a candidate symmetric equilibrium would be characterized by the probability with which rational leader sends a message to each backup. So now we are switching to symmetric strategy. This is why we have just one probability for each backup. And the leader sends message to each backup with probability P. Then rational backup who has received a message forwards this message with probability Q. Now, after this peer-to-peer communication stage, the backups collect the number of messages that they got, and a committing rule is part of the equilibrium, where a backup commits if it receives some number of messages, including one from the leader, and possibly a different number of messages when he did not receive a message from the leader. Okay, and this is going to characterize an equilibrium. Now, what we are showing is that we always can get a non-consensus equilibrium where no matter what messages are exchanged, all nodes decide not to commit. But we are really interested in consensus equilibria where the messages are sent around, and we ask under what conditions we can get an equilibrium where the system achieves consensus. For any candidate equilibrium with given P and Q, and in environment characterized by a number of nodes N and a number of measure of faulty nodes F, a node receiving a certain number of messages can make a couple of inferences from the number of messages that it received. So first of all, for given P and Q, if the leader is rational and sends messages for probability P, and all rational nodes are forwarding the messages with probability Q, then any node is going to receive a number of messages within a very well-defined interval between n minus f times p and q and n minus f times p and q plus fp. So the difference is whether, if all rational nodes behave according to the equilibrium, the difference in the length of this interval is what do the Byzantine nodes are doing, whether they are sending or not sending their messages outside of what the protocol in a way would be prescribing. So if a node, rational node, knows that this in a given candidate equilibrium, this is the interval that is consistent with rational leader, then receiving any message, any number of messages outside of this interval directly tells him that the leader must be Byzantine. Okay? Now, for the number of messages within the interval, we cannot say for sure whether the leader is rational, because Byzantine leader can also mimic rational leader. So there is still uncertainty whether the leader is Byzantine or rational. Now, the second thing that the node can infer from the number of messages that it receives is the number of messages other nodes are receiving. And this again depends on the behavior of Byzantine nodes. And basically, for any number that a rational node is receiving, it knows that a number of messages that other nodes are receiving are within a certain bound. And if the leader is Byzantine, that means that other nodes are receiving plus or minus f of the messages, right? So that means that if I'm a rational node and I have received less than f messages, I know that other rational nodes, other nodes can receive f more messages than me, but also some other rational nodes may get 0 messages because they can get f my number of messages minus f, and that would be, it's of course is bounded by 0. Those two inferences are going to help us or they are actually helping the nodes to make a decision, the commit decision that would be the best response and is going to get us to the equilibrium. So, like I said, if a rational node received less than f messages, then the node knows that some of the other rational nodes may get 0 messages. If they get 0 messages, they may be, they just cannot commit, no matter what their strategy is, they cannot commit to message that they never received. And if there is a positive measure of those nodes, potentially positive measure of those nodes that do not commit, the best response for me is not to commit as well, because as ambiguity aversion, I'm taking the worst case scenario. So I'm not going to commit if I got less than f messages. Now we can use the iterated elimination of dominated strategies. We started with f, but we can iterate it further. If I get 2 f messages, by the same token, I know that there may be some positive measure of rational nodes that got f or less messages. They are not going to commit, so therefore my best response is not to commit as well. And we can iterate it all the way until we get to the other side of the interval that is consistent with the rational leader. So how do we know that we are always going to get on the other side of the interval? This is because the interval is no longer than f. And therefore, since we can iterate by f's, we are going to be able to go on the other side. Now, if there is some positive measure of nodes that are not going to commit because they got too many messages, that for any number larger than this, I'm also going to consider possibility that there will be some other nodes that got fewer messages than me, and they are not, but in this red interval, they are not going to commit, and therefore I'm not going to commit. So with that, I'm never going to commit a message for the interval that is consistent, for which I know that the leader is Byzantine. Okay? So I'm never going to commit there. How about the interval where the leader may be Byzantine or rational? So first of all, we show that either for the whole interval we commit or we don't commit. Then there's always an equilibrium where we just don't commit because there's just zero coordination equilibrium. But most importantly, we show that there exists equilibria where we commit whenever we get the number of messages within this interval, and it depends on the relative value of the reward and the penalty, as well as the probability that the leader is Byzantine versus rational. And we derive the particular conditions under which those equilibria exist. And we fully characterize all symmetric equilibria. We find the conditions on the parameter space, and then we look at the possible equilibrium strategy. Okay. So now you can agree that those are really cool equilibria. This is a really cool game, and we had a lot of fun finding the results. But the question is, why does it matter that we find this equilibria? And what we want to argue is that we already know that operational success of any blockchain depends on its design. And there is large research literature on the proof of work design of the blockchain. We have heard about other design choices in proof of stake. And what we are doing is we're showing that accounting for incentives in Byzantine Fault Tolerant consensus, which should be accounted for if we are talking about blockchain environments and not just distributed databases deployed within particular company. If we account for incentives, then we show that all designs are subject to multiple equilibria concerns, and the equilibrium selection is a real problem. And then the existence of kind of good consensus equilibria depends on the relative value of the rewards and penalties or punishments. And yes, we can basically either say that maybe those parameters are restricted by their environment, or like Silvio Micali, we can throw our hands and say we're not going to set those parameters because they are too difficult to set, and we're just going to maybe look for some other randomness in the environment. But it can also be a decision of the system designer, and our results may help guide those decisions rather than doing it by trial and error or saying that it's too difficult. So, to summarize, we developed an economic framework to analyze incentives in Byzantine fault tolerant protocols so that they can be used in the context of blockchains, which should provide a guidance for maintaining reliable distributed ledgers among the self-interested parties rather than just honest nodes. And in our framework, we are focusing on information imperfection rather than maybe operational costs that are also playing a role in maintaining those distributed systems, right? And the information imperfection is something that is difficult to take away. This is an intrinsic challenge in distributed systems, in peer-to-peer systems, where decision needs to be made based on local information. Thank you.